In this series of videos, we're going to learn about drag. The goals for this video are to define and distinguish resistive forces, which include friction and drag, define the drag model, calculate drag forces, and define terminal velocity, otherwise known as terminal speed. Student learning outcomes for this section will include problem solving. Drag is due to the motion of an object through a medium, most commonly air. It's very complex and depends on the object's speed, its shape, and the density of the medium through which it moves, which, as I mentioned before, could be air, water, oil, some other sort of viscous medium. Now, the properties of drag are essentially that it's always going to point in the opposite direction of motion. That's the sort of definition of a resistive force. So just like friction, which will oppose motion, causing an object to try and slow down if we're talking about kinetic friction, drag will do the same thing. So one way to think about it is like friction due to the air or the medium that you happen to be traveling in. And because those particles are touching a much larger surface area of the object, instead of just the point of contact between, say, an object and a table, drag ends up being much more complex. The one key thing, though, is that it increases in magnitude as the object's speed increases. Due to the complexity of drag, we're going to use a simple model. In this simple model, 3 conditions must be met. Otherwise, we will not be able to use this particular model because it means that the situation that we're examining is too complex for us to do for this class. The first condition is the object must be moving through air near the Earth's surface. So if we have Earth's surface down here, the object must be relatively near the Earth's surface. We're not talking about something out in space, like a spaceship or anything like that. The reason behind this is that the air pressure and the amount of air that an object will be traveling through differs depending on how far away you are from the ground. So most of the time we'll be assuming atmospheric pressure, which based on where we live is pretty a reasonable assumption to make. The other thing that it assumes is that the air near the Earth's surface is all roughly around the same temperature. Yes, we have seasons, and it's warmer at sometimes and cooler at others, and this does play a role in things as well, but it ends up being a relatively small part of what's going on. But in general, if you are at much higher altitudes, there'll be much larger changes in temperature, which we would be not accounting for properly if we were examining a situation at that point. The second condition is that the size of the object, we can call that its diameter if we're talking about a circular object, but essentially the largest distance from side to side needs to be somewhere between a few millimeters and a few meters. If it's too small, then we have more complex particle issues to deal with, and if it's too large, then our particular model will break down as well. The third condition is that the object's speed is less than a few hundred meters per second. What we're going to be going through in modeling is not going to necessarily be speeding bullets, for example. We can model objects that are relatively fast, but there's still going to be some limitation on that, because as you get going to high enough speeds, there's other conditions that can happen if you're reaching speeds that would, say, break the sound barrier. So as long as we're meeting these 3 conditions, this particular model that I'm about to show you will work generally for balls, people, cars, etc. Most of the objects in our everyday world, as long as we don't go too extreme. So this equation is how we'll go through and calculate drag, and we're going to go through each of these symbols and variables in turn. Now the first one, of course, is velocity here. And velocity is the one we're going to start with because that's the one we know so much. Now, since it doesn't have the arrow over the top, we're actually just looking at the magnitude of the velocity, which is speed. Now, unless that speed is a constant, our drag force is not going to be constant. And this is very important because it means that we will not be able to use any of our kinematic equations when working drag problems if the drag force, and realistically, if the net force is not constant. So There will be specific situations where we can use those, but in most instances, because drag will not be constant, we will not be able to use kinematics to work the problems. If you need to go from acceleration to a velocity or velocity to position, you will need to use calculus in order to make those changes. The second symbol that we have here is the capital C. This is known as the drag coefficient, and it has no units, so it's known as a dimensionless number. So you wouldn't have anything like meters per second, anything like that off of it. It's just going to be a number, 0.3, for example. And this drag coefficient is going to be different for every object because it's dependent on the shape of the object itself. More aerodynamic objects will have a smaller drag coefficient, and more clunky objects that are not very aerodynamic will have a much larger drag coefficient. I'll show you some examples on the next slide. The next one in line there is the lowercase Greek symbol rho. Rho is the density of air, and its value changes based on altitude and temperature. This is what we were referring to on that most recent slide. So most of the time, we're going to use 1.3 kilometers per meter cubed for this density of air. And that is the value at atmospheric pressure, essentially at sea level, and if the temperature is 0 degrees Celsius. Now the final symbol in our equation here is A. A is the cross-sectional area of the object. We can think of that as the biggest amount of area that the object would face if it were going into the wind, so to speak. So for most objects that we will utilize in these problems, we'll either be given a cross-sectional area and given the drag coefficient C, or we'll be given something that we can approximate to a simple shape, like a sphere or a cylinder or a square or a cube. So I've got some examples here, and let's go through and take a look at these in a little bit more detail. Now the first one that we have here is a sphere. So again, the cross-sectional area is, imagine cutting this in half at its widest point. If you do that, that's giving us our cross-sectional area. So for this particular sphere, we can see that that's going to be this circle here. And so the area of that circle is going to be pi r squared. The corresponding drag coefficient that goes with it is about 0.5. Now, the thing that's interesting is that drag coefficient corresponds to the overall shape. So I could consider having maybe a different shape. Maybe this actually has a cone out on the front. And it still would have the same cross-sectional area because the widest point where I cut it is still that circle. But I've made this shape more aerodynamic now. So this green shape might have a coefficient, a drag coefficient that would be smaller than 0.5. And we can see the same sort of things for the other ones. I could make any of these a little bit pointier and in theory more aerodynamic. And therefore the corresponding drag coefficient for that particular object might be different, even though that cross-sectional area happens to be the same. A great example would even be comparing the cross-sectional area of the sphere and the cross-sectional area of our first cylinder. Both have the area of a circle, pi r squared, but clearly have different drag coefficients due to the difference in aerodynamics between the two shapes. The third example that I have here is our cylinder falling side down. So if I rotate my cylinder, I can make it so that it has an even larger cross-sectional area than it did when it's vertical. So now my cross-sectional area is going to be the 2RL. So this length right here is the diameter, 2R, and then this direction is going to be the length of that particular cylinder. So we can see that the cross-sectional area there is just a rectangle. So usually you'll be going through and dealing with cross-sectional areas that are something like a circle, a rectangle, a square, or even a triangle. So if you can find a cross-sectional area that looks something like one of those similar shapes, that's going to be the closest that you're going to get for most of these problems. Again, because we're simplifying them as much as possible.